In the last part of today's lecture, we're going to talk about a different kind of model that is structurally a little bit similar to a variational autoencoder, but can be a lot simpler to train. So here's the idea. Instead of having the decoder represent a distribution over x given z, we'll actually have a deterministic decoder. We'll have a decoder that directly turns z into x. Not a distribution over x, but actually just a single x. This might seem like a subtle and very small change, but it actually has very profound effects on what the resulting model looks like. Why is it such a big deal? Well, because now, if we want to compute p of x, or log p of x for training, we can use the change of variables formula. So the change of variables formula says that if x is a deterministic function of z, then p of x is equal to p of z times the inverse of the determinant of df dz. Okay, that formula looks a little bit arbitrary, where z is given by f inverse of x. The formula looks a little bit arbitrary, but intuitively what it means is that if you have some distribution over z, and z is transformed in a deterministic way to get x, then to get a density over x, all you have to do is modify the density over z by how much the volume changes according to f. So there's quite a bit of kind of differential geometry that goes on behind the scenes to explain this formula. I unfortunately don't have time in this lecture to get into the details of that, so you kind of have to take me at my word that this is the expression for this density. But a little bit of intuition for why it might be true is, if you imagine that z is, let's say, a uniform distribution on a 0 to 1 interval, and x is on interval 0 to 2. So that means to go from z to x, you need to blow up your values by a factor of 2, which means the density drops by a factor of 2. So if you're doubling all of your values, then df dz will be 2. When you invert, you get 1/2. So the intuition here is that f essentially expands or contracts the volume, and you have to account for that expansion or contraction, and that's what the determinant term accounts for. So that's kind of the math behind it, but for practical purposes, what this formula tells us is if we can calculate the determinant of the Jacobian df dz, and we can calculate the inverse, f inverse of x, then we can implement a model of this sort with a deterministic function that maps z's to x's. So the determinant is just a correction for the change in local density due to f. And this is really interesting because if we can somehow learn invertible mappings from z to x, that can make this determinant easy to compute, and we can build these kinds of models without having to worry about all that variational inference stuff. The model can actually be much, much simpler, conceptually at least. No more lower bounds, and we can get exact probabilities and likelihoods rather than just bounds on probabilities. Okay, so let's unpack this a little bit. This class of models is sometimes referred to as normalizing flow models. Our training objective is just maximum likelihood. Maximize the log probability of all the xi's in your dataset, where we use the expression from the change of variables formula on the previous slide to write p of x instead in terms of p of z. Now, p of z is still some very simple distribution, like, for example, a zero mean unit variance Gaussian, which means if we substitute this formula into the training objective, our objective is log p of f inverse xi. So that's, for example, a zero mean unit variance Gaussian evaluated at f inverse xi, minus the log determinant of df dz. The reason it's minus is because you need the inverse of the determinant, so when you take the log, it becomes a minus. And what we're going to do is we're going to choose a special structure for the neural net that represents f that makes f inverse and that determinant easy to calculate. And then we can skip all of that complexity with variational lower bounds. So a normalizing flow model consists of multiple layers of invertible transformations. So all we need to do in order to implement these types of models is figure out how to make an invertible layer, and then compose many of these invertible layers to make a deep network. So what I'll discuss in this part of the lecture is just how can we make an invertible layer, Composing multiple invertible layers is very easy. So the determinant of their composition is just a product of their determinants, which means the log is just a sum of their log determinants. Okay, so our function f of z will be a neural net with multiple layers. We can call those layers f1, f2, f3, f4. If we have 4 layers, for example, and we just need each of those layers to be invertible. So if each layer is invertible, the whole thing is invertible. And oftentimes, if we can make the function invertible, invertible functions will also have very convenient determinants. Not always, but oftentimes they will. So the hard part is basically making it invertible. Once we make it invertible, we can usually see what the determinant is, and it's something fairly simple. And the log determinant of the whole model is just the sum of the log determinants of the layers. So our goal will be to design an invertible layer and then compose many of these invertible layers to get a fully invertible neural net, which we can use to represent f. So there are many different ways to design invertible layers. I'll start with one of the simplest types called nonlinear dependent components estimation. But just keep in mind that there are many different choices in the deep learning literature, and I'll just cover some simpler choices. But if you're interested in this question further, there's a lot more that can be said about normalizing flows that I have time to cover in this lecture. Okay. So here is a simple type of invertible layer. Ordinarily, a layer in a neural net would be some mapping, and I'll just say that it's a mapping from z to x, some kind of special transformation. Importantly, here I'm going to describe the case for one layer, but in reality, of course, we'll have many of these layers. So a normal kind of layer that we learned about might be x is given by a ReLU applied to wz plus b, right? That's kind of a regular affine or linear layer followed by a ReLU nonlinearity. But we can't use this because this is not invertible, because the ReLU will zero out all the negative portions and we can't recover those. So you can go from z to x, but you can't go back from x to z. So this is not invertible. So here's an idea. What if we force part of the layer to keep all of the information so that we can then recover anything that was changed by the nonlinear part? Here's what we can do. Let's take our z and let's split it into 2 parts. We'll say that the first part is like the first d entries in z. So d, z1, z2, etc. out through zd. So we take the first d numbers in z, and that's the first part. And then the second part is zd plus 1 through n, right? That's just the rest of z. And x will also have 2 parts. And the first part will just be copied directly. So x1 through d is just equal to z1 through d. It's completely unchanged. And then we'll also take that first part and we'll additionally pass it through some neural net. Maybe that neural net is just like the one above. It's just a ReLU applied to w times z1 through d plus b. So some kind of nonlinear function. And then we'll add that to the second part. So xd plus 1 through n is going to be equal to zd plus 1 through n plus this nonlinear part g theta. So g theta is just that neural net part. It's a lot like a residual unit, except that we split it in half. We have the first half that just copies and the second half that has this nonlinear component added to it. So g theta doesn't have to be invertible here. It can be like a ReLU or something like that. A ReLU applied to a matrix multiply. Okay, so g theta of a might be just ReLU wa plus b. Some kind of nonlinear operation. So my claim is that this is invertible. So here's a question for you. If you have x, can you recover z? If so, then this layer is invertible, which means that you can compose multiple such layers to form a normalizing flow model. If you feel up to the task, you could pause the lecture right now and try to work out on your own how to invert this layer. In order to invert this layer, all you have to do is figure out, given x, how do you recover the z that created that x? So you can pause the lecture now and try to work it out on your own. And once you've done that, you can continue watching and I'll explain how to do this. Okay. So here's the process. Now, to go backwards, we have x and we need to figure out z. So step 1, recover z1 through d. You know that z1 through d is just equal to x1 through d, so recovering that is very easy. Step 2, recover g theta of z1 through d. Recover that neural net part. And once you've recovered that, then you can recover the second part of z by taking the second part of x and subtracting off the neural net part. So that's how you can compute the inverse of this layer. So the trick that we needed to make this work is that the first part is preserved losslessly, and the nonlinear component depends only on that first part, which means that you can recover the nonlinear component and subtract it off. So this is how you can calculate the inverse of this layer. It's an invertible layer. Okay, now what about the Jacobian? What about this determinant of df dz? Right, we need that to compute our normalizing flow objective. Well, both x and z have these two parts, the first half and the second half. So if we want to write out df dz as a matrix, that matrix has 4 blocks. The top left block is the derivative of the first half of x with respect to the first half of z. The top right block is the derivative of the first half of x with respect to the second half of z. The bottom left block is the derivative of the second half of x with respect to the first half of z. And the lower right block is the derivative of the second half of x with respect to the second half of z. Okay, so what is the top left block? What is the derivative of the first half of x with respect to the first half of z? Well, x1 through d is just equal to z1 through d, which means the derivative is just identity, right? It's just a diagonal, it's just a matrix with ones on the diagonal and nothing else. Very easy. What is the derivative of x1 through d with respect to z d plus 1 through n? First, what's the derivative in the lower right? X d plus 1 through n with respect to z d plus 1 through n. Well, that's also just identity, right? Because x d plus 1 through n is equal to z d plus 1 through n plus something that doesn't depend on it, so that derivative is identity. The top right block is 0, because the first half of x doesn't depend on the second half of z. The bottom left block is something complicated, because that's the part that goes through the nonlinear neural net. But if you want to calculate the determinant of this matrix, now those of you that remember the formulas for determinants might realize at this point that the determinant is not affected by the lower left block because the upper right block is 0. So the determinant for a matrix like this is a lower triangular matrix. The determinant is just determined by the diagonal entries, and the diagonal entries are all 1. So since the Jacobian looks like this, the determinant is just 1. That's very convenient. So because of this particular form, for these invertible layers, the determinants are always 1, which means that that term in the objective has no effect on training the model whatsoever. So this is very simple and very convenient. Unfortunately, it's representationally a bit limiting, because we can't change the scale. The determinants always being 1 means that this kind of network only transforms these into x, but it never rescales them. So it can be very difficult to train very complex distributions in this way. It's a very convenient architecture, but it's not a very expressive architecture. So in practice, what we see is if we take this kind of invertible layer and we stack a few of these layers and use them to train a generative model, we can do a pretty good job of modeling simple data sets like MNIST digits. So the digits on the left look like kind of real digits. We can do kind of an okay job with simple face images, so they kind of look like faces. But when we start looking at more complex images, it tends to break down. So the SVHN dataset, the one shown on the left, is actually also a dataset of digits, but they are color digits taken by photographing house numbers. And you can see there already the model is starting to struggle. If we train on CFAR10, which has a variety of different images of realistic objects, we get very low quality images. So the model is pretty limiting. There's a small change we can make to this model that makes it substantially more expressive. And this is something called Real-NVP. NVP stands for non-volume preserving transformations. So here's the idea in Real-NVP. We're going to split z and x like before into 2 parts. And the first part, just like before, will be copied. But now we'll have 2 neural nets. We'll have a scaling network and a biasing network. So we'll take the second half and we'll actually multiply it by the first neural net, and then we'll add the term from the second neural net. So that the second half of x is given by the second half of z times the exponential of the output of the first neural net plus the second neural net. And the reason for the exponential transform is just to make it positive. And it's not enough to use a ReLU for that, because you really don't want any zeros creeping into that. Because if you multiply some part of the second half of z by 0, that information is lost. So you really need to always multiply by numbers greater than 0, which is why you need that exponential transform. And this is just an element-wise product. So this is also an invertible operation. The way you derive the inverse is very similar to before. You recover the first half of z by just using the fact that it's equal to the first half of x. And once you've recovered that, you can recover g theta and h theta. And then you can solve for the second half of z by just taking the second half of x, subtracting g, and then dividing by the exponential of h. And that's why it's so important to not allow those multiplicative terms to go to 0, because then you'll get a division by 0, and of course that's not allowed. So this is still invertible, but now the Jacobian has a much more interesting form. The top left block is still identity, but the bottom right block now is the diagonal of these exponential values, which means the determinant now is much more interesting. The determinant is not 1, it's actually a product of those diagonal terms, and the log determinant is their sum. So this is significantly more expressive at the cost of adding a second nonlinear component, and this can generate much higher quality images. So here are examples of samples generated by the Real-NVP model. So they look much more realistic on much more diverse and complex data sets. Okay, so some concluding remarks about normalizing flows. One big advantage of normalizing flows is you can get exact probabilities or likelihoods from them. You can actually evaluate p of x, which you cannot do with a variational autoencoder. A variational autoencoder will give you a bound on p of x, but it will not give you the exact probability p of x, whereas a normalizing flow will. You don't need any lower bounds, and it's conceptually somewhat simpler. But it also has a few major disadvantages. First, it requires a special architecture, so you can't just use regular layers for it, you have to use these special invertible layers. The second and perhaps more subtle point is that since each layer is invertible, the dimensionality at every layer has to stay the same. And this can be a really big deal with high-resolution images. If you have like 1,000,000 pixels in your image, then you need 1,000,000 dimensions in Z. Whereas a variational autoencoder can have a latent code that is much, much lower dimensional than the image. And this can be a major limitation.